Hi everyone, welcome to my Physics 2 HPO Programming Introduce video. So this video has three parts. The first part is I want to introduce my triple pendulum mathematic theorem report. Second, I want to use VPython to show you a moving video, like a diagram. And the last one is I will show you 3 experiment video to have a check whether my experiment is roughly matched my theory report. Okay, so now let's start the first part for the triple pendulum. Okay, in this theory report, in the introduced part, I want to show you that according to the analyze to the double pendulum, we have the triple pendulum based on the knowledge from the single pendulum then to the double pendulum. The pendulum, I should say, is like a noisy system. If we have only single, it's not. If we have more than two, equal or more than 2, we will have a noisy system. So this theory report will investigate triple pendulum and the Euler-Lagrange equation. So here we have 3 parts. The first is fully defined triple pendulum, and the second is to derive its Euler-Lagrange equation. The last one in this theory report, we will provide some real number just to put the data in my model, so then I can show you the diagram. So okay, the firstly is to introduce my fully defined triple pendulum. We can have a look like this graph. So first is we have a coordination, and then we can have like 3 board here, 1, 2, 3. And for this triple pendulum, I only have rigid line. So like here, I have line 1, line 2, and line 3. And also we have a angle. The angle here is the line and the vertical part, the vertical line here. So the angle is between them. Okay, so we have theta 1, theta 2, and also a theta 3. Then we can use the Euler-Lagrange equation to find all factor we need according to my graph here. So the first is I need to have x1, x2, x3, y1, y2, and y3. Okay, then we get, because if we want to use a Euler-Lagrange equation, we need to know what it is. So Euler-Lagrange equation have, I can say, have 2 parts. Is just everyone knows the L equal K minus V. The K here is the kinetic energy. I also show it here. And we also have a potential energy. The potential energy should be V, is named V here. So the first is the kinetic energy. It look like this equation. And then we can output with some more detail. And then we can have a V here. Also the equation and some output. Then we use the Lagrange. Is L equal K minus V. And we get this formula here. And next is, because if we want to use Euler-Lagrange equation, we know there are 2 parts and they are equal. The first part is dl over d theta, and the right hand should be d over dt and have a bracket times the bracket. The bracket inside should be the dl over d theta dot. The theta dot should be the theta derivative. So I also show it here. Have a look. This is the left part of the equation, and some right part of the equation I have spoke it before is something here. So we have the theta, we have theta dot, the derivative, and something here. So everything for each theta, I have the equation, and then I can calculate the Euler-Lagrange equation for theta 1, theta 2, and also theta 3. So then the second part has finished. So now we can to put some real number in my formula, then to use Mathematica to give me the graph. It's obvious and make it easier to understand. So like here, the first I need to choose some real number or define my triple pendulum. So I give the m1, m2, m3, they're equal to 1, just a unit. And the g is 9.8. And L, I choose 0.2, 0.2, and 0.2, because in the final experiment, I also choose 0.2, 0.2, and 0.2 meter. Okay, so I choose, that's the reason I choose 0.2. And then I can solve the Euler-Lagrange equation. Something is very automatically here. And then I can get the plot here. But the plot is not very easy to understand, so I change to another plan. So we can have a look like this one. So we can have a look for the first one, first ball here. It's, if we don't look at this 2 part under it, this one, it's really like just a single pendulum. It's good. It have good look. But after we add the second one and third one, it's very noisy. And some you have a look, some line here go up, and very shape, right? Very shape here and not symmetric. So this is my theory here. Finally, according to my real definition and the data give it, I get some graph like this. So for my triple pendulum, the mathematical notebook have shown up. So the next part I want to show you, because when I do the program, I find at that time I also learned the Vipassana and phys1 course. So I also write a pattern coding. You can have a look like this, also define something. So now let's run the graph just to have a look whether it's noisy when we have the second one. Yes, you can have a look. This one is very noisy, right? It's okay. It's not symmetric. It's, I guess it's noisy, especially the third one. We take the time longer, but there is a problem. Just it look like it's symmetric, right? I have asked teacher for that problem here, because the logic in behind the pattern is just use Euler Lagrange, and it's roughly some detail is lost. So if we use mathematical the notebook, the math behind it will be well defined. So it look like more, it look like better. So I've showed that one. So the last part here, I want to show you the experiment video. There are three. The first one's here. We can have a look. We can have a look at this one. Okay, 3, 2, 1. Let's go. You can have a look at the very beginning. Maybe we can watch it. And here, because it's the real pendulum, 3, 1, and the tension in the line will change, and it's like jump up and down. So it's not like theory prediction I have made, something like this. So we can have a look at the first experiment again. So just to focus on the maybe the first 3 or 4 seconds. Let's go. Yeah, it's very noisy. You can have a look. It's really like the graph or the line, the curve I gained from the notebook or the Vipassana. Okay, so then we can have a look for the second one. 3, 2, 1, go. Yeah, this one is very noisy. When you can have a look when it go up here. And in the end, because the mass, the some friction, some jump or tension change in the line, it's not good in the end. So it's very not noisy, but we can go back, have a look for the second part again. Yeah, you can have a look. It's noisy, and I think the not regular jump and down or the curve here is could be match my mathematical prediction. Okay, this is the third one. Then we have a look for the last one. Okay, this one is pretty good. It's obvious it's noisy, right, in this part. But in the end, still, because it's the real world, so something is not very physical. So we can have a look here. When it go down, it slowly, we can have a look. Yeah, it's, if I have a curve or draw some line here, I'm sure it will be match my mathematical notebook or Vipassana. Maybe from here it's not really good, but if we go back, try again, have a look. It's noisy for the second and the third bore. But you can have a look from here to here. The line is not very straight. Sometimes I think the tension will be changed here. So that's also the reason why in the end it's not very fit my theory. I think that's the problem. Okay, so if I need to do some conclusion, I must say the mathematic part will be better. It's because it's the formula and the math we used behind the coding should be well defined. And if we use something like the Vipassana here, although I write some coding to do this, but somehow I can say it's noisy, right? It's not the same for each part. But if you take the time longer enough, it look like symmetric, maybe not correct. And for the real experiment, at the first 3 or 4 seconds, I'm sure it will match my prediction, no matter the mathematical notebook or the Vipassana. But because the real world, some tension in the line have changed, and the mass, and also some air friction, something else maybe do it manually, so something changed. So in the end, like at the second, the 20th second, maybe not useful. So that is my HPO Physics 2 project. Hope you enjoyed the video, and thanks for your watching.